Welcome back, guys. In this video, I will be trying to dive into the world of elves. It's not elves like you know them in the fairy tales and that kind of stuff. Actually, we will be diving into the world of binaries. So yes, it's time to start getting into the binaries world. The first thing that I want to show you is or that I want to talk about is the compilation process. So we need at first to look at it process. So this is actually the compilation process of let's say of a binary. I don't want anything like complicated. I want this is the most simple thing that we can look at. Okay, so actually before getting any kind of binary, let's suppose you are just like having, I don't know, you'll be trying to code any kind of code. Let's say you are, for example, I don't know, let's say for example we have a code.c that you will be run. Okay, there is a pre-existing code. Let's say it's going to just printf I don't know, just hello world or something. Hello world. um, yeah, okay. So let's try to compile this code. So we have code.c-o code. So actually when you do ll code, this is actually the binary that we have. When we do a file command can give you information about the binary that you will be having. So when we click or when we do a file code or when we run the file command, we get that this is actually the format of the binary, which is an elf. So basically, how did this binary got built or got built? So this is mainly what we will be trying to learn in this video. We'll be trying to dissect elf binaries, understand how they are created, and how can we try to go back. This is actually will be in the next videos. But actually we will dive like in practical ways on how to reverse engineer any kind of elf binary we would be having. So yeah, so the process of compilation of compiling any kind of binary is important because if you don't know how even something got built it, you won't understand how we can do the reverse engineering. So that's why we need to dissect what is happening or to dissect the binary itself. So we have to understand at least um, how this binary got built. So the first thing that we have to do is the pre-processing, which is the source code. Actually, a lot of what is happening now is actually done by the compiler. For example, when I did GCC, GCC is a compiler actually, which is the GNU compiler of Linux, for example. So GCC done a lot of stuff for us, but I wanna actually just understand a little about the pipeline that is happening in here. So the first step is the pre-processing. So you are actually pre-processing the source code in C, and then you are compiling the code to an expanded source code, and then you are doing something called assembling. And assembling actually is done actually using an assembler. So that, for example, is doing what we call is assembling, but it's actually assembling what exactly? So it's assembling the assembly code generated by the expanded or generated by the compiler itself. So the compiler's main job is to take your high level code, such as, for example, this one, and try to compile it into assembly language, for example, MoviEX, EBX, etc., etc., etc. And then, just after assembling that assembly code, we would get something called object code, which is just after the process of assembling. So, once we got the object code, we have to make an executable file, which is the elf in our situation. But before just making the executable file, we need to link the libraries in the executable. So for example, when I just called for example, stdio.h. Stdio.h is actually a library, so that's why we will be needing a linker just to link the functions used by that library into our main code. So yeah, so this is basically how the pipeline is working. And right now, I will be trying to focus um, on that little elf binary that is generated by the compiler. So we'll try to dissect this executable in this video. So yeah, so I think we have just pretty toughly understand the exact VE in the previous video, but at the end of the most paths, like as I said in the previous videos, the kernel will reach a final program that contains machine code for it just to launch, which is that binary. So typically a setup process is just required before just actually jumping to the code. And for example, different parts of that program have to be loaded. I mean, for example, in this code, different like parts of that code have to be loaded into the right places in memory, and each program needs how do we say this? Each program needs like different amount of memory for different things. So we have standard file formats just to specify how to set up a program for execution. While, for example, Linux just supports many and many formats. Like the most common formats by far is the ELF, which is the executable linkable file. So yes, so basically this is what happening. And in the Linux kernel, ELF binaries are handled by the bin format ELF that I have mentioned in the previous video, are actually handled by this code. So which is a more complex than any other kind of handlers that I have seen in the kernel code, and that contains actually thousands of lines of code. And actually, this is the code that is responsible for parsing out, I think, certain details from the ELF file and using them just to load the process into memory and execute it. So yes, so this is basically what is happening. So now let's try to dive more deep into the ELF itself and try to see the file structure of any kind of binary we would be dealing with. So let's try to do like ELF structure. Uh, okay, this is a good picture or a good image. So um, so just before just looking at this picture, let's try to look just at the design of the elf binary. So at first we have the elf header, and then we have the program header table, and I will try to explain each one of them. And we have the dot text, and we have the read-only data, etc., etc. And we have a section header table that points to those sections, and the program header table is also pointing to those sections. Also, the he's actually pointing to the sections dot text dot read only data and data. So yeah, he's actually pointing to the sections. Yeah. Let's go back to the elf header. So I think that every elf file actually has an elf header, and it has the very important job of conveying the basic information that's about the binary, such as, I don't know, for example, what a processor it's designed to run on. I don't know, for example, the ELF files that contain machine code for different processors type like ARM86. I don't know. uh, I think it has also like the binary is meant to be um, I don't remember this correctly, but I think it has also informations about whether the binary is meant to be run on its own as an executable, or whether I think it's meant to be loaded by other programs as, I don't know, for example, dynamically linked libraries will be explaining that, or I will be trying to explain that later on. But for now, just we will go just into details about what this elf header is doing. So yeah, so the entry point of the executable is actually the elf header. So the later sections, like the sections under the elf header, specify exactly um, where the text is and where the data is uh, into the memory, I think. I don't remember that too. Actually, there is a lot of points that I don't remember in that in this structure, but I think it's time to get them back. Yeah. So I will be trying to remember with you, like just recording the video and remembering the stuff. Yeah. So I think the elf header is always at the start of any file, as the structure is mentioned, and it specifies the locations of the program header table and the section header table, and the sections headers too, which can be anywhere within the file. So basically, those tables um, in turn points to data stored elsewhere in the file. Yeah. So let's start just by digging deep into the program header table. So the program header table is actually, I think, is a series of entries containing specific details um, just for how to read, to load and execute the binary at runtime. Just we can see, for example, common, I think just the common program header table types, I think. Yeah. So basically, as you can see, this is the program header table. It actually has a lot of entries, and each entry has its own specific job. So for example, the pt load means it contains like data that should be loaded into the memory. For example, this pt loads points to the data that should be loaded. um, for example, what do we have also? We have, for example, the PT node. I think this means that the segment that contains like some kind of informations or text that shouldn't be necessarily be loaded anywhere, I think. Yeah, so each entry like specifies informations about where its data is in the file, and sometimes how to load the data into memory, I think. So it points to the positions of its data within the ELF file itself. So each one of those entries is pointing to the position of its data within the ELF file. I will be trying to give an example later on. I'm just trying to explain the job of this table exactly. So it can specify, like for example, what virtual memory addresses the data should be loaded into memory add. Um, and this is typically left blank, like for example, if the segment isn't meant to be loaded into memory. Um, we have also two fields, like just to specify the length of the data to be loaded, one for the length of the data in the file itself, and one of the length of the memory region to be created. So if the memory region length, for example, is longer than the length in the file, the extra memory will be filled, for example, with zeros. And actually, this is beneficial for programs that might want a static segment of memory to use at runtime. And these empty segments of memory are typically called the BSS actually segments. So finally, like after just loading any kind of data into the memory or any kind of segment, a flag field specifies what operation should be permitted if it's loaded into memory. So, for example, we can just have, for example, the PF R, which is making it readable. We have also the PF um, write just to make it, for example, writable, and we have also the pf, for example, execute just to make it, for example, executable. Yeah, it means, for example, when you try to load the dot let's say the code of the program into the memory from the elf, you will find, for example, um, the code of the whole program in the .text section. So when you try, for example, to load the .text section into the memory, you will try eventually to add the flag X and, for example, R to that segment of code when you are trying to load. So this is basically just to say to the CPU, hey, you are allowed to execute this segment of code, etc., etc., etc. Yeah. Now, let's go back to the section header. So we have the section header that contains, for example, the .text, the read-only data, and the other kind of stuff. So, and we have also a section header table. So the section header table is a kind of series of entries, also like the program header table, but it contains information about sections specifically. So this section information is like, I don't know, a map. Yeah, it's like a map. Um, and this map is like mapping the data inside the elf file. So it makes it easy for programs like, I don't know, for example, debuggers such as GDB, to understand like the intended uses, I think, of different portions of the data. So, for example, if the program header table can specify a large I don't know, a large data to be loaded into memory together, that single, for example, pt load in the table, in the in the program header table block might just contain both code and global variables, but there is no reason for those to have to be specified separately just around the program. So the CPU just starts at the entry, it just starts at the entry point and steps forward, just accessing data when and where the program requested, for example. However, I think the softwares like a debugger for analyzing the program just needs to know exactly where each area starts and ends. Otherwise, it might try to decode some text that says, for example, I don't know, hi iron bite or this kind of data, and since that isn't valid code, this information is stored actually in this section header table too. So while it's usually included, the section header table, I think, is actually optional because elf files can run perfectly well with the section header table just completely removed. And I think developers who want to hide what their code does will sometimes just intentionally try to strip the section headers just table from their elf binaries just to make them harder to reverse engineer maybe. So I think each section now has a name, and we should explain just the names why they are like that, but section has its own job. Yeah. So for example, the .text contains machine code to be loaded into memory and executed on the CPU, for example. Um, and actually, there is called, actually it's a word actually called the SHT um, prog. I don't remember exactly. Is it prog bits? Yeah, I think it's prog bits. SHT prog bits, I think type or something. Yeah. Actually, this is like a flag just to mark the executable. And there is also another flag called the SHF exec something. I don't remember like the rest, but they are flags just to mark that this section is executable. And for example, there is also, I think, the allocation we can do, like just using another flag, which is shf allocate, just to, for example, um, allocate a flag, or means that this section, when it's loaded into memory for execution, um, it will be just executed, or we can allocate that into the memory. Yeah. But just don't get confused by the name because it's dot text, that does not mean it's the code. Actually, the dot text contains just the code that will be loaded into the memory. Yeah, just don't get confused by the name. I think it's still just binary machine code. I think I always also just find it somehow strange that it's called dot text, and despite not being readable as a text. We have also the dot data, which is actually containing the initialized data hard-coded in the executable to be loaded into memory. So, for example, I don't know, a global variable containing some text, for example, might be in this section. For example, I don't know, when you try to let's just say you have this and you try to create a new variable that can, for example, char x, I don't know, 2023 contains hello world, or I don't know. This actually hello world will be contained in this section, or in the data section. So yeah, it has also um, its own section, and it has its own flags too. We have also the prog bits, which is also of a type of a prog bits, which means that the section contains informations about for the program. Its flags actually are also the allocate. But this now, I think we should be having the SHF of the write, means that it's writable. It's writable. Yeah. Um, We have also the BSS section, which is really interesting too, which is the .bss. So the .bss actually, guys, is the common way just to have some allocated memory that starts out zeroed. For example, it would be a waste to include a bunch of empty bytes in the L files, so the special segment type called the BSS is used. For example, it's helpful just to know about, for example, BSS segments during debugging. So, for example, there is also a section header table, just entry, that specifies the length of the memory to be allocated. Um, it is of a type SHD no bytes, actually, and that's not now prog bytes. So, and its flags are the allocation and the write. So yeah. So basically, for example, um, when you initialize, for example, a variable x like that, actually that x will be going to the BSS. Yeah, because it's not initialized. So there is another interesting section, which is the read-only data. This is like data basically, except it's read-only, and in a very basic like C program, for example, that runs printf, for example, hello world, like the string hello world would be in the read-only data section, while the actual printing code would be in the dot text section. Now, I think this is now pretty explained. So, yeah, there is one other like section that I remember, which is the .shs, I think tier tab, is it like that? I don't remember the name, but this section was interesting actually. Yeah, so this function, guys, is actually a funny implementation detail. So the names of the sections themselves, um, like for example the dot text, the read-only data, etc., aren't included directly in the section header table. So instead, each entry contains an offset, for example, to the location in the L file. So that contains its name. So this way, each entry, for example, in the section header table can be the same size, for example, just making them easier to parse. And an offset just to the name is a fixed size number, where we just have to include the name, I think, and the table. Just we would be using a variable size, I think, string of a string, and all of this name data is stored in its own section called the SHR tab. Yeah, and we will be giving the type of str tab. Now, let's just try to explain a little about the data. So, since we have sections, since we have sections and we actually have the um, the program header table, which contains the offset of a lot of program, okay, program header table. Um, Actually, let's say we have like a program header table entry of, for example, I don't know, just an example. Let's say, for example, the type is, for example, PT interrupt. Let's say it's PT interrupt. Actually, um, this program header table entry, which is the PT interrupt, is used just to know where the interpreter is exactly. We will be trying to explain what the interpreter is doing. But let's suppose it's just, for example, containing the offset or the path and the data of the interpreter. For example, just lib, I don't know, 32. Um, just an example of an interpreter. For example, the LD Linux. I don't know, for example, 86. Um, just an example. It does not have to be like 100% correct. Let's say it's just a shared library. I'll be trying to explain that too later on too, what a shared library or what a shared object is exactly. Example 2. So basically, let's say there is like a data section. So this is where we find all the data. So there will be something like this one, and data is basically linked like to each other. There is no spaces between them. Let's say there is, for example, hello ironbite. Let's say, for example, there is also dot I don't know, data, for example. And there is, I don't know, for example, a bunch of other data also. So this is just some random data. Okay, so this is basically what is the data of the binary. So when we actually try to see the program header table, it's going, for example, to see at this entry point there is the PT interrupt, and the data of that PT interrupt is actually this data. So basically, the program header table will be having all the offsets of that thing. So for example, it will be pointing to that thing and the data. And for example, let's say we also have in the program header table another type, which is um, I don't know, let's just say we have um, the PT, for example, the PT load, yeah, just the PT load, yeah, and the data actually be will be the hello world or the hello iron byte. Yeah, so this is actually where the hello world will be pointed by. So the PT load will be pointing that hello world in the elf. So this is basically just a brief explanation about the program header table and the structure of an elf. You can just keep on researching that on the internet if you want, but this is just a brief idea. So now I'll be trying to explain a little about a concept called linking, which we also like see in this. Yeah, the linking phase. Yeah, it's time to just explain a little the linking. So just back to the binary format of code, I think that I have been like mentioning in the previous video. Like I don't know if we could go back. I think it's okay. Never mind. So the kernel, I think, just cares about two types of entries in the program header table, which are the PT load, which are the PT load, um, which are the PT load and the PT interrupt. So this is the two entries that the kernel has interest to. Um, Actually, the PT load segments will be specifying where all the program data like the .text and the .data sections need to be loaded into memory, and the kernel just reads these entries from the alt file just to load the data into memory so the program can be executed by the CPU, I think. And then the other type of a program header table entry, which will the kernel will be interested to, is the PT interrupt, because it will be specifying the dynamic linking runtime. So just before we start talking about the dynamic linking, let's just talk about linking. So in general, programmers actually tend to build their programs on the top of libraries and reusable code, just for example libc, which we talked about earlier. For example, when running your source code into an executable binary, a program called a linker resolves all these references by just finding the library code and copying it, for example, into the binary. So this process is actually called static linking. So, which means there is no external code to be included um, in the binary when it's running, and we will be trying to including the external code directly into the file, and then we will be trying to distribute distribute that file to the people. Yeah. So, however, just one thing to mention in this point is some libraries are super common. So you will find something called libc, for example, that is used by basically every program under the sun. So since it's the most like famous interface for interacting with the operating system through syscalls, um, it would be terrible just to use it would be just terrible just to use that space to include a separate copy of libc in every single program on your computer. So it might be nice if bugs in libraries could be fixed in one place rather just when having, I don't know, a bunch of bugs in each binary that is included with the copy of that specific libc. So this is why we have invented, or they have invented, dynamically linking. So it's a kind of solution to this kind of problems. So if a statically linked program needs a function, for example, dog, um, let's try to draw a little. So if, for example, there is a program one, this is program one, this is program two, just to explain what statically linking mean. So, and there is a function called dog. Let's say dog is in another library, for example, I don't know, let's just call it iron. So it's in a library called iron. Yeah. So when we try to statically link the dog function into the program 1 and into the program 2, we will actually um, get a whole copy of the entire dog function. So we will be trying to get the dog function here and the dog function here, and there will be a whole definition of the dog function in the program 1 and the program 2. We'll be taking the whole implementation into the binary itself. So if it's, for example, dynamically linked, it will only, for example, include a reference to the dog. For example, in the program 1 and in the program 2, it would be having a reference to dog. So for example, a reference to dog, and we will be having a reference to dog. And here you may have other code, other code, other code, other code, and here you might have other code, other code, other code, other code, and so on. So when the program is run, dog is like hopefully just installed on the computer, and the dog function's machine code can be loaded into memory on demand. So this is will be happening when we are working on the dynamically linking. So this is a dynamic linking, and this is a static linking. So whenever we are talking about static linking, we are taking the whole code of the dog function, and when we are trying to talk about the dynamic linking, we are just taking the reference of the dog function. So this is basically what is happening. Now, let me just try to explain more what is the dynamic linking doing, since it's really fascinating. So on Linux, dynamically linking is just trying to link the linkable libraries, like for example dog that I have mentioned, um, which are typically packages like into files, for example, which we call them shared object actually. So for example, dog should be like dog.so, which is a shared object. So it's a kind of extension that describes this specific kind of functions or this specific kinds of packages. So these .so files, I think, are just L files. Just like programs, you may recall that, I don't know, the elf header includes like just a bunch of fields to specify whether the file is executable or a library, if you remember that in the elf header. So the elf header is specifying whether this executable is going to be executed or is it going to be a shared object. So how can we identify that? We can just check the elf header of that specific file. So yes, so for example, I don't know, we can have also with the shared objects such as this dog function or this dot shared object, sorry, we can find also something called dynamical a dynamic symbol section. So a dynamic symbol section is in this section header actually table, which contains informations on what symbols are exported from the file and can be dynamically linked to. So, for example, on Windows, I think I have read about something that says that we actually know them. That, for example, libraries like, I don't know, dog, when they are converted to Windows, you actually know them under the extension .dll. And in the Mac operating systems, you find them under the extension of dynamic lib, like that. So I think this is basically what happens. So, for example, just like Mac operating system apps and Windows executable files, these are like just formatted slightly differently from ELF files, but are the same concept and technique, I think. So, I think an interesting distinction just between the two types of linking is that with static linking, I think um, only the portion of the library that are used are included in the executable, and I think when we try to load that into the memory. So with dynamic linking, which is the other way, I think the entire library is loaded into the memory. So this might initially sound less efficient, but it actually allows like modern operating systems just to save more space by loading a library into memory once and then just sharing that code between processes. Only code can be shared as the library, and I think only that will be making the library needs different state for different programs. For example, you only need to just load one time the library needed, and multiple processes will be using the same library, but the saving can still be on the order like, I don't know, for hundreds of just megabytes of RAM or something like that. Yes, I think this is it. So um, now let's go back to the execution. So let's go back to the kernel, just imagining the kernel now is running the alpha. So if the binary is executing, it's dynamically linked. Um, is trying to execute just with the method of a dynamically linked. It means that it was compiled like dynamically linked. So the operating system can't just jump to the binary code just right away. Um, and because there would be missing code, just remember when we try to dynamically link programs, we only reference the library functions that we need. So that's why to run the binary, the operating system, I'm sorry, needs to figure out what libraries are needed. Just try to load them, replace all the named pointers with actual jump instructions, maybe to the actual functions. Like this is a very complicated code that interacts deeply with the ELF formats, I think. So I think it's usually the kernel, or it's usually a standalone program, yeah, a standalone program that do this part to the kernel. So elf file specifies the path actually to the program they want to use, like typically something like that I actually just used, which is for example the interpreter now. So the interpreter job is to give the kernel an idea on how to interpret the whole binary. For example, when you have references to other libraries, etc., etc. So the interpreter job is to interpret those references for the kernel. So yeah. So just after reading the elf header and scanning through the program headers table, the kernel now can set up the memory structure for the new program. So it starts just by loading the PT load segments into the memory, just trying to I don't know how to say, so how do we say this? Okay, so it's just trying to make the program like try to load the static data, the BSS space, the machine code, which is the dot text um, section, which is in the dot text section. Um, and if the program is dynamically linked, like the kernel will have just to execute the elf interpreter. So it also loads the interpreter's data and the BSS and the code into the memory too. So now the kernel just needs to set the instruction pointer for the CPU to restore when returning to userland. So for example, if the executable is dynamically linked, the kernel sets the instruction pointer, I don't know, for example, to the start of the elf interpreter code in the memory. Otherwise, the kernel sets it to the start of the executable. So the kernel is almost like the guy who is doing all of this and is almost ready to return from the syscall. Just remember, don't forget that we are still in the exec VE until now. So it pushes the argument count and the argument vector and the environment variables to something we call stack for the program just to read when it begins. So the registers are now cleared, for example, and before just handling a syscall, the kernel stores the current value of registers to the stack to be restored when just trying to switch back to the user space. So this is basically how the elf binary um, is executed. So finally, just the syscall is over and the kernel returns to the user land. It restores the registers which are now zeroed and jumps to the stored instruction pointer that was already stored. That instruction pointer is now the starting point of the new program, um, or for example, the elf interpreter if he was going to use an elf that was dynamically linked, and the current process has been replaced. So yes, so this is like pretty much what is happening underneath when you are trying to use elves, and you can research more on elves if you want to. ELFs, like ELFs, or I don't know how do you call them, but you will pretty much see them a lot when trying to reverse engineer any kind of binary that has been produced by Linux. So yeah, so I think it's a good time just for you to keep on researching on that too. Yeah, so I think we have hit the end of this video, so don't forget to subscribe, don't forget to ask questions. Yeah, if you have any kind of question in your head, throw it in the comment sections, and bye.